Hello everyone. So today I'm going to present our paper, that is PAcT, Detecting and Classifying Privacy Behavior of Android Application. So developers are often required to provide privacy notices to the users so that users will be aware to know how and why their information is being used. So in order to do so, developers usually use policy generators to generate privacy policies, one way of providing privacy notices. However, these policy generators often do not capture the true privacy behavior of an application. Thus, as a result, the generated privacy policies become inconsistent with application's actual privacy behavior. Moreover, developers often use third-party libraries to provide certain services without properly being aware of their privacy configurations. These third-party libraries accessing users' personal information might also affect the application's privacy behavior. In many cases, developers often do not include privacy notice as a part of software engineering artifact, and thus many applications don't even have any privacy notices. In previous work, several research have been attempted to identify inconsistencies between an application and its privacy policies. Such as a series of work by Jain et al. Actually identified that there are inconsistencies between an Android application and its privacy policy. And by inconsistency, I mean that your application is collecting your location, but it is not even mentioning it in its privacy policy. In order to address this challenge, several works have been attempted to generate consistent privacy policies based on either questionnaire or predefined templates. However, to the best of our knowledge, none of this work actually resolve the inconsistencies, or they do not provide any traceability. And by traceability, I mean that the generated privacy policy does not have any link with the application source code. In order to address these research gaps, in our previous work, we introduced an approach called PRIGEN. So what PRIGEN does is it identifies and extracts code segment that uses personal information. In this work, we call such code segment as permission returning code segment, or in short, PRCS. After extracting PRCS, PRIGEN basically translates it to its corresponding privacy captions. And here, privacy captions are short descriptive sentences that are describing the privacy behavior of a certain code segment. For an average length of 4 to 5 lines of code, we actually achieve very good accuracy. However, and this approach actually provides us traceability because we know which source code has been translated to which privacy caption. And it also resolves inconsistency because the privacy caption is generated directly from the source code. However, we faced some challenges, such as the accuracy started decreasing when the length of code started increasing. Also, if we want to train a large deep learning network, we actually require a high-quality large dataset that is 1, time-consuming to annotate, 2, it requires huge manual effort. Moreover, privacy perception may vary based on individual to individual. In this case, creating semantically similar privacy captions for a certain code segment can be challenging. To address these challenges, as well as maintaining consistency and providing traceability, in this work, we propose PAcT, or Privacy Action Taxonomy. PAcT basically aims at identifying privacy behavior of a mobile application. In our work, we focused on Android-based mobile application. So the question can arise that what do we mean by privacy behavior? In this work, we consider privacy behavior of a code segment is the practice and purpose of using that information. So by practice, I mean that how a code segment uses your personal information, and by purpose, why the code segment is using this personal information. So PAcT basically provides us a lot of benefits, such as it may include a set of labels that can describe practice and purpose. So an annotator can basically use these labels to annotate the code segment that actually elevate the privacy subjectivity. Also, since we will have a set of labels, it is easier to label a code segment than generating semantically similar captions that might require a lot of time to do. PAcT basically includes 3 important steps. First, we need to identify the labels that can actually describe the practice and purpose of a code segment. Then we are aiming to conduct experiments to see that if we can automatically identify those labels in a code segment, then we analyze the results to find out the limitations or rules that we need to work in the future. So let's talk about the identifying the labels. In order to identify the labels, we focus on PRCS, or permission returning code segment. Let me discuss a little bit about what PRCS is. So in Android application, if we want to access a certain information, we basically need to use Android API. In order to preserve privacy and protect privacy of an individual, this API requires permission to be mentioned in manifest.xml. So what we do is we identify such code segments that call such permission recurring API, and we call such code segments in general permission recurring code segment or PRCS. So a PRCS can have multiple methods linked via call graph, and each method can be referred as hop. So for example, first hop is the first method that is calling the permission recurring API, and the second hop is the second method that is calling the first hop to call that the first hop that is calling the permission recurring API. So in our work, each PRCS can contain up to 3 hops. Why? Because in our primary analysis, we actually analyze that 80% of the time information has been used within the 3 hops of our PRCS. We also developed our in-house PAcT static analysis tool and use that tool to extract PRCS from Android APK files. So in next slide, I'm going to discuss how did we identify the labels from the PRCS that can describe the practice and purpose of an Android application. So we basically followed the conceptual to empirical approach that has been introduced by Nicholson et al. And which is widely adopted to basically develop any kind of taxonomy. So first, we actually we basically collected an initial set of labels from several privacy regulations such as GDPR and CCPA, and also Apple's privacy nutrition label. Then we used our PAcT static analysis tool to extract a set of PRCS. We analyzed the labels. We looked for certain end conditions. If the end conditions meet, then we will stop the process. Otherwise, we will update the label set, and then we will extract another set of PRCS, and the whole process continues until we meet any end conditions. The end conditions could be no new label can be introduced, or we don't need to update the current label set. After we meet any end conditions, we basically finalize our label set. The whole process, including the end conditions and the iterations, everything is available in our paper. If you're interested, you can just go over it. So after 3 iterations, we basically identified 4 levels for practice and 4 levels for purpose. The first level for practice is processing, that is when a personal information is being used to provide certain information. For example, a ride-sharing application might collect your location, and it might use this to provide nearest ride. The second level for practice is sharing, that is any third-party library is accessing that Android API. The third level is collecting, that is the accessed information is being saved in any off-device location. Apart from these 3 levels, we also decided to have another level other, when the usage of the personal information is not clear to us. Similar to practice, we also identified 4 different levels for purpose. The first level is functionality, when the information has been used for the app's functionality purposes, such as location, payment, or authentication. The second purpose level is basically advertisement, when the information has been used for advertisement purpose. And the third is basically analytics, that is the information has been used for analytical purpose, such as crash analytics or user analytics. Similar to the practice, we also introduced another level, that is other, for purpose, when the purpose of using the personal information is not clear to us. So now we have 4 levels for practice and 4 levels for purpose. The next stage for us too, we wanted to annotate certain PRCS with these 8 levels. So for that, we relied on Android dataset. It is a very popular dataset that has more than 3 million Android APK files. We extracted randomly 15,000 APK files, and then using our PAcT, we basically extracted 180,000 PRCS. The first 2 authors of the paper, using our in-house annotation tool Coder, that I will come a bit next, we annotated 5,200 PRCS with the identified levels for practice and purpose. It is to be noted that each PRCS can have more than 1 level. I mean that one PRCS can have sharing and processing as practice level, and also can have advertisement and analytics as purpose level. Now the question can be, how did we annotate the code segments? How did we understand that a PRCS can have basically sharing level or processing level? We basically defined a set of heuristics. The details are in the paper. Let me briefly explain, go over it. So we basically looked into a lot of cases, such as the name of the classes, the method, the API name, as well as the description of the API. We also traced the flow of the information within the hop as well as the between the hops. We also looked into the types of the third party. For example, if the third party is for advertisement purpose or if the third party is an analytical third party. Let me walk you through an example to understand it a bit clear. So this is one PRCS. The blue box denotes the method, that is get connection Wi-Fi info, and the red box basically denotes the Android API that has been called by the get connection Wi-Fi info. In this example, that is get connection info. And the green box basically the variable that is storing the information that has been received by calling the Android API. Now, if we take a close look at it and analyze the flow, we can notice that this information has been used to get the MAC address and IP address of the device, and it has also been returned to further hops. So from these analyses, we can conclude that the practice of accessing this information is processing. We can also label sharing because the class name and the APK names are not same. And that means that the code segment is from third party. If the code segment is supposed to be from first party, then the class name will be derived from the APK name. And the purpose we have labeled this as advertisement because the third party library is an ad library. As I mentioned earlier, we used our in-house annotation tool Coder. The reason we did not use any existing tool because to the best of our knowledge, no existing tools actually provide annotation for source code. Coder basically helps us and supports us in various ways. You can basically do classification, translation, and annotation tasks. Multiple annotators can actually work on the same project. And also you can you can have control over the annotator's roles and you can define certain permissions. And also you can host the tool in a private server that can also ensure your privacy. So this is the user interface of Coder. As you can see, the code segments fit perfectly, and it is true for any programming language. We also provide the APK metadata, and the metadata includes various types of information such as the APK name, class name, and the method name, as well as the API that has been called. We also provide the API description that is similar to the description available in Android public documentation. We can also see the collapsible bar for second and third hop. And you can also see that we have label drop-down box that has basically the labels and that we have identified for purpose and practice. You can also see the guideline dialog box. So any annotators can, during the annotation time, can just look into the guideline to get some idea. There is also a navigation button that will help any annotators to go back and change the annotation that they have done previously. So using this annotation tool, we have basically annotated 5,200 PRCS as I mentioned earlier. Now the next step for us to conduct certain experiments to answer 2 research questions. The first research question focuses on what is the baseline accuracy to identify individual practice and purpose labels in a code segment. And the second research question focuses on if we increase the number of hops, if it has any impact on identifying individual practice and privacy levels in PRCS. So in order to actually answer these research questions, we need to develop 2 different datasets for each of these research questions. So first let's discuss about the dataset that we developed for research question 1. So as I mentioned earlier, research question 1 focuses on baseline accuracy that to identify individual practice and purpose levels. Remember that each level, practice and purpose, each of them has actually 4 levels. So we have in total 8 levels. And our PRCS can have more than 1 level annotated to it. But here we are only focusing on identifying individual levels. So in total we have 8 levels. So we decided to actually develop a 8 binary dataset. So the question that may arise that how did we make the binary dataset of a code segment that is already annotated with multiple levels? So let me give an example to it. Let us consider that there is a PRCS that is labeled with sharing and processing. So what we do is, we first make a copy of it, and for sharing binary dataset, we consider sharing as positive and all the other labels that are not assigned to it as negative. For processing, the same principle has been followed. We consider processing as positive and all the other labels that are not assigned to it as negative. It is also need to be mentioned that for research question 1, we only considered course segments from first hop. Now let's talk about research question 2. Research question 2 focuses on that if increasing number of hops have any impact on identifying individual practice and purpose levels. We have in total 3 hops as I mentioned earlier, and we have total 8 labels. So we have in total 24 binary dataset. Now the question is, how did we make the dataset? First, we collected all the course segments that we used in research question 1 that has up to 3 hops. We filtered them out, and if any course segment has more than 1 label assigned to it, what we do, we actually follow the same principle we did for the research question 1. For sharing dataset, binary dataset, we basically consider sharing as positive and all the other labels not assigned to it as negative. And this is true for 3 hop samples. And another thing to be mentioned that in for research question 2, we have first hop that has only course segments from first hop, second hop that will have a course segment from both first and second hop, and third hop will have course segment from first, second, and third hop. Once we developed the datasets, then we extracted AST paths and binary labels, and we fed it to a simple RNA network with PRCS embedding, and we calculated our metric scores and derived confusion metrics for research question 1 and research question 2. This is our model architecture. We have embedding layer that is embedded with the AST paths. Each AST path has 3 tokens, and then we basically concatenate these 3 tokens into a single vector, and then we feed it to a fully connected layer F1. Then we use the output of the F1 as to 2-layer LSTM model, and then basically we use the hidden state of this LSTM as an input to our output layer F2, and then we passed it to a sigmoid optimized function to optimize the binary classification and prediction. Now let's discuss some results that we found interesting and we wanted to share with you. So let's first discuss the result for RQ1. Research question 1 focuses on the baseline accuracy to actually identify practice and purpose levels, and this is the result for both practice and purpose. And from the table, we can see that across the label types, we found good F1 score for the collecting, that is 79.62%. And for purpose, we found a good F1 score for functionality, that is 79.02%. Now let's take a closer look at it. So for collecting, that is a label for practice, if we take a close look at the confusion matrix, we can see that 84 samples have been identified as true positive and 67 samples has been identified as true negative. That basically demonstrates that our model is optimized and it is not actually biased towards any positive and negative samples. But we actually received a bit different result for analytics, that is a label for purpose. We noticed that we got F1 score 66.88%, and it is again, let me recall you that for research question 1, we only considered the first hop code samples. And the confusion matrix shows that our model is biased towards the positive samples. One reason we did not receive the moderately good result for analytics could be that it is from basically third-party libraries, and often cases third-party libraries basically uses the information in further hops. Now let us discuss the result for research question 2. And as I mentioned earlier, research question 2 focuses on if increasing number of hops have any impact on model's performance while we are actually predicting the individual levels for practice and purpose. So this is basically a result for the practice, and we can see that we actually in first hop for processing we received 58.75% accuracy. But once we basically gave the additional information, that is the second hop, the accuracy increased a bit and we received 64.75%. However, the accuracy decreased a little bit once we actually introduced another hop, that is the third hop. So the reason could be processing is a very complex task. So you need to look at different cases such as the calculating your location or changing values or retrieving certain information. So it might be one of the cases that we did not receive better results for processing. However, okay, so for sharing, we noticed that the more hops we have introduced, the model could predict better, actually perform better. So for example, for sharing, in first hop, we received 65.1% accuracy. We introduced another hop, the accuracy increased, and we received 67.1%. And then we introduced further hop, and then we actually received 71.09%. Which is pretty good, and it also aligns with our understanding that sharing is basically the code segment from third-party library, and it might be the case that third party is basically using this information in further hops. For purpose, this is the result for the purpose labels, and we can see that we are getting pretty good accuracy for the functionality, and that is 86.97% in second hops. And the accuracy slightly decreased in third hop. So one of the reasons could be that functionality is basically the first party code segment. So they might have basically used this information within the first two hops. And if you remember the result for analytics and analytics for the research question 1, from research question 1 to research question 2, we actually received better result in further hops. That is 78.83% in both second hops and third hop. That actually also aligns with whatever we are assuming. That is, it might be that the third-party code segments are using your information for analytical purposes in further hops. And this is the confusion matrix for the processing level. And as I mentioned earlier, that processing is a complex level to predict, and it would be worth exploring that what are the features that have been used to actually predict and why we are getting such a result. And for functionality, we received, if we take a closer look at the confusion matrix, we can see that our model actually predict a false negative and false positive for the lower amount of code segments. That actually shows the effectiveness of our model. In conclusion, I want to say that yes, we introduced an automated approach that could actually detect privacy behavior in Android application. And to the best of our knowledge, we are the first one so far to develop a taxonomy to identify privacy behavior specifically in source code. And we also annotated 5,200 code segments with the practice and purpose levels that we have identified. And we conducted experiments with 8 datasets in 4 configurations. And we actually achieved better F1 score 79.62% and 79.02% across the level types. For future work, as I mentioned earlier, each PRCS can have at least more than one level, and in this work we only focused on understanding if we can predict the individual level. So in future, we want to conduct multi-level, multi-class classification experiment, and we also focus on using larger models such as convolutional graph neural network. And we also noticed that for certain levels, we are getting better result, and for certain levels, we have to sort of compromise. So we also want to see that what are the features that have been used for classification tasks, and for that, we are planning to actually study attention. And this overall framework is focused on helping developers to generate accurate and consistent privacy notice. So we also aim at conducting user studies with developers to know that how do they actually perceive the effectiveness of our framework. With this, I conclude the presentation, and I'm open to any questions.
Thank you. Do we have any questions? You mentioned on future work already that you will be looking into multi-class, multi-label classifications. Are you intending to look at all combinations of different labels, or specifically the cross product between purpose and practice? If so, if there's a specific cross product of purpose and practice labels, do you identify any combinations that are particularly sensitive or that would be the typical okay category? So if you look at the multi-label, multi-class, what specifically are you looking for?
That's a great question. So in future, we are actually planning to look into all the labels rather than cross products, because you know that a core segment has certain practice and purpose. So we actually want to look into that if our model can predict like multiple levels for both practice and purposes. So we are not actually looking to the cross product. We are looking into all of levels.
Do you have any preliminary data, any teaser of, would that probably improve accuracy? Do you think that if you actually look at multi-labels, that you could get even better results? Or is it going to be even more challenging because you've got less data samples for those combinations of labels to train on?
It's an interesting question. I might have to look at it. I don't have the answer at this point, but that might be the case that it might also, our dataset might also, if we change certain bits such as, we actually used, for research question 1, we actually used the first 100 AST part, and for research question 2, we randomized the AST part. So maybe in future, if for the same dataset, we change the combinations of the AST part, that might also actually improve the accuracy, but this is something worth exploring.
Do you expect that you will need to manually annotate even more samples to get sufficient data size for training for the combinations of labels?
I don't think so at this point, but even if it requires manual annotation, I think annotating labels are like more time efficient than actually generating privacy captions or something. So, and we also have our in-house tool, so which is user friendly, so that should not be a very big challenge for us.
Okay. Any other questions at this point? Yes, please.
Thank you. If you can go back to one of the confusion matrix slide, the very first one, it was very interesting. Not many research teams show the false negatives. I appreciate presenting that because it has value, not only just showing the positive results, but negative results help folks not to try in those areas. So I appreciate that. But one of that had like 101 and 105 as, for the analytics. You mentioned the true reason for such high false negatives is some third-party libraries. Can you clarify more or expand more on it? Like, what is the primary reason for such high false?
So, I most probably did not actually explain it better, I think. So for the confusion matrix, I mentioned that our model is a bit biased towards the positive samples, but if you look into the analytics, that is basically the level for purpose, we received 66.88% F1 score, which is definitely not a very good one, but this is something we can see that we can improve maybe in future. So one of the reasons could be that because analytics are basically third-party libraries, which means the third-party code segments are basically accessing this Android API. So maybe that the third-party libraries are using those information in further hops. And if you look into the result for research question 2, where we basically used first, second, and third hop, the result of the analytics actually improved. That is 78.83%. So that could be actually a reason that we're not sure about it yet, but this is something worth exploring.
Thank you.
Any other questions? Not at this point. Again, if you have later questions, please just reach out through digital channels. Thanks again to our speaker.